So today we will discuss the one of the important gadget which you use in the circuit. Now that is the piezoelectric sensor, or it is a piezo sensor. In the last lecture we have discussed the piezo transducers, but here we discuss the piezoelectric sensors. When a sensor works on the principle of piezoelectricity, it is known as the piezoelectric sensor. Piezoelectricity, that is a phenomena where electricity is generated if the mechanical stress is applied to the material, and that means that the sensor work when we apply the mechanical stress on the sensor, then it produces the electricity. Now what is the piezoelectric sensor? Is sensor that employs the piezoelectric effect to measure the variations in the acceleration, strain, pressure and the force by converting them into an electric charge. That is the piezoelectric sensor. And this piezoelectricity produced is proportional to the stress given to the substrate or the material of the strong piezoelectric crystals. Means we have a piezoelectric material and on which the stress is given, then the piezoelectricity is generated, which is proportional to the stress given to the material or the substrate or the substance which we are using. Before discussing the sensors, we discuss what are the difference between the transducers and the sensors, because we have discussed the piezo transducers. Now how it is different from the transducers. The sensors basically senses the physical quantities and converts them into the signal read by the instrument. On the other hand, the transducers converts one form of the energy into the another, and transducers converts electricity to the electromagnetic waves, while the sensors senses the physical quantity and converted it into a analog quantity. Apart from this, if we take the example of the transducers, then we have the antenna, microphones and loudspeaker, and in the sensors examples we have LED, we have touch sensors in the automobiles, pressure switches, like that we use in the sensors. Now if we take the transducer, then it converts the measured quantity into the standard electrical signal, like minus 10 to the plus 10 volt DC, but this sensor measures voltage, capacitance, inductance and the ohmic resistance. Now you see on the screen that these are the difference between the transducers and the sensors. So the sensors which senses the signals and then it converted, then transducers it converts the sensors give the physical quantity and it converts the one form into the another. So piezoelectric sensor is a sensor which is based upon the piezoelectric effect, and it is a self generating and electromechanical conversion sensors. And if we say that is sensitivity element is made of piezoelectric material. Whenever we talk about the sensors, then we just keep in the mind that the material which we are choosing must be having the high sensitivity, high stability, and in this manner we can say that the piezoelectric sensors are the self-generating and electromechanical conversion sensors, and its sensitive element is made of the piezoelectric material. When the piezoelectric material is subjected to the force, electric charges are generated on the surface, and after the charge is amplified by the charge amplifier for the photoelectric, and the impedance is transferred, and it becomes the electric power output which is proportional to the external force. Means external force which we applying, on the basis of that we can get the electric power output. So the piezoelectric sensors are used to measure the non-electrical physical quantities after the force and the energy are converted into the electricity. Means we are converting the force and energy into the electricity through the piezo sensors. and its advantages are wide frequency bandwidth and high sensitivity, high signal to noise ratio, simple structure, reliable operation and the lightweight. Apart from that, it is having some disadvantages that the some piezoelectric materials require moisture proof measures, and the DC response of the output is very poor in this case, which requires a high input impedance circuit or a charge amplifier to overcome this effect. And now we discuss the piezoelectric sensor circuit. The circuit we will show in the diagram, and it consists of internal resistance Ri, which is also known as the insulator resistance, means we require the resistance. Another, we require the inductor which is connected and produce the inductance due to inertia of the sensor, means we require the resistance R1, we require the inductor, and apart from that we require the capacitance which is Ce, and which is inversely proportional to the elasticity of the sensing material. Now, to obtain the complete response of the sensor, load and the leakage resistance should be larger enough such that the low frequency is maintained. So, you see on the screen that this is the diagram of the piezoelectric sensor, and you are having the impedance, capacitance as well as the we have resistance. So, and it is connected with the battery which is represented by the P. Now, now you see that the actual sensors are represented by that. It is having a positive terminal and negative terminal, and you are seeing the size. It is in miniaturization in the size. It is very small size, so that it can be used in the smaller circuit. Moreover, presently we prepare the nano sensors, and that will be prepared by the printing electronics or by using the other means like lithography and all that. So, this is the circuit of the piezo sensor. Now, we discuss the working of the piezoelectric sensor. As we know that when a pressure or the acceleration is applied to the PZ material, that is the piezo material, an equivalent amount of the electric charges get generated across the crystal faces. Electric charges will be proportional to the applied pressure and applied force or applied acceleration. So, piezoelectric sensor cannot be used to measure the static pressure. At the constant pressure, the output signal will be 0. It means we are using the variation in the force, variation in the pressure if we measure the output through the sensor. So, the output signal will be 0 in case of the constant pressure. The working of the piezoelectric sensor can be summarized by step. The first step is that in a piezoelectric crystal, charges are exactly balanced in unsymmetrical arrangement also. Number 2, the effect of the charges cancel out with each other, and hence no net charges will be found on the crystal faces. Number 3rd step is when the crystal is squeezed, the charge in the crystal becomes unbalanced. Hence, for now on, the effect of the charge does not cancel with each other, which make net positive and negative charge to appear on the opposite faces of the crystal. So, it will generate the positive and negative charges of the crystal. Therefore, by squeezing the crystal, voltage is produced across the opposite face, and that is known as the piezoelectricity, that is converting. You see, these are the steps. You are seeing the steps that first there is a positive negative charges, after that they are connected, then positive and negative, then we squeeze it, then positive negative charges are collected on the surface and it would work accordingly. And in the next, what we have, that piezoelectric effect that sensor is based upon the piezoelectric effect. That piezoelectric effect, in the short time duration we will discuss it, that what is this piezoelectric effect, and it is discovered by 1880 by Jacques and the Marie Curie during the studies into the effect of the pressure on the generation of the electrical charges by the crystal, and that crystal was the quartz. This piezoelectricity is defined as a change in the electric polarization with the change in the applied stress. Means when we apply the stress, then the change in the electric polarization, that is a direct piezoelectric effect. The converse piezoelectric effect is a change of the strain or the stress in the material due to the applied electric field. Means we have a two type of, one is direct piezoelectric, second is a converse piezoelectric. In the direct, when the pressure is given, the polarization changes. Now, in the second, the stress generated due to the applied electric field. So, the linear relationship between the stress, that is Xik, applied to the piezoelectric material and the resulting change density is defined as the Di, which is known as the direct piezoelectric effect and is written as Di directly proportional to Xjk. And Di, small d is defined as the coefficient. So, directly proportional, as it is Di directly proportional to Kjk, Xjk. So, Dik is the directly proportionality constant. So, where Dijk is a third rank tensor of the piezoelectric coefficient. Another interesting property of the piezoelectric material is that they change their dimensions when an electric field is applied to them. Means it may be contract, it may be expand whenever the force or the pressure is applied to the sensor. This converse piezoelectric effect describes the strain that is developed in the piezoelectric material due to the applied electric field is defined as Xij is equal to dkij ek. Now, where T denotes the transport matrix, because D transpose I j k. You see that it is a converse. So, it is defined as the unit of the converse piezoelectric effect is a meter volt inverse. So, the piezoelectric coefficient D for the direct and the converse piezoelectric effect are thermodynamically identical, that is defined as D direct is equal to D converse. So, the sign of piezoelectric change Di and the strain Xij depends on the direction of the mechanical and the electrical field respectively. It means it is, as we defined in the previous lecture, that the piezoelectric transducers work on the three directions like longitudinal, transverse and shear. So, similarly here that the piezoelectric charge Di and the strain depend on the direction of the mechanical and the electric field respectively. The piezoelectric coefficient D can be either positive or the negative, that depend upon the direction and how we are working on it. So, it is a common to call a piezoelectric coefficient measured in the direction of the applied field the longitudinal coefficient, and that measured in the direction perpendicular to the field, that is the transfer coefficient. Means it depends upon direction. So, the piezo coefficient which we are measuring through the direction, and if it is applied in the direction of the field, then it is a longitudinal coefficient. Otherwise, if it is applied direction perpendicular to the field, then it is a transverse coefficient. Other piezoelectric coefficients are known as the shear coefficients, means it may be applied in any direction. Because the strain and stress are symmetrical tensors, so the piezoelectric coefficient tensor is symmetrical and with respect to the same indices, and it is defined as Dijk is equal to Dikj. Dijk is equal to Dikg. So, the strain and stress are symmetrical tensor, and the piezoelectric coefficient tensor is symmetrical with respect to the same indices. The microscopic origin, as the piezoelectricity generated, and it is a microscopic origin of the piezoelectric effect is the displacement of the ionic charges within a crystal structure. So, as we know that the piezoelectricity generated, how it is converted, how it is generated the piezoelectricity as the pressure is applied on it. So, we know that displacement of the ionic charges takes place within the crystal structure, and in the absence of the external stress, the charge distribution is symmetric and the net electric dipole moment is 0. Now, these are the steps how the electricity is generated when the mechanical stress is applied. The first, piezoelectric displacement of the ionic charges within the crystal structure we will measure. Then, in the absence of external strain, then the charge distribution is symmetric and there is no change in the electric dipole moment. When an external stress is applied, the charges are displaced and the charge distribution is no longer symmetric. They are randomly distributed and the net polarization is created. So, in some cases, a crystal possesses a unique polar axis even in the unstrained condition. So, this can result in the change of the electric charge due to the uniform change of temperature, and this is called the pyroelectric effect. The direct piezoelectric effect is the basis for the force, pressure, vibrations and the acceleration, and the converse effect for actuator and the displacement devices. And so, the elements, so now the thing, if we talk about the piezoelectricity, then the material plays a very important role, because we are preparing the direct piezoelectric sensors as well as the converse piezoelectric sensors. In the direct piezoelectric effect, on the basis of that we produce a sensor. If the converse, we prepare the actuator. So, we have the piezo transducers, we have the piezo sensors and we have a piezo actuators. Now, all are depend upon the material, the symmetry which we are using. So, symmetry is very important in any preparation of the piezo sensor, transducer or the actuators. So, element of the symmetry that are utilized by the crystallographers to define the symmetry about the point in the space. For example, the central point of the unit cell, a point, center of the symmetry, axis of the rotation, mirror planes and the combination of these we use in the preparation of the piezoelectric sensor. Now, utilizing these symmetric elements, all crystals can be divided into the 32 different classes or the point groups. So, 32 groups are having the subdivisions, and we are having a 7 basic crystal symmetry, in which we have a triclinic, monoclinic, orthorhombic, tetragonal, rhombohedral, that is a trigonal, and a hexagonal and so on. So, in the cubic of the 32 points groups, 21 classes do not possess a center of symmetry. So, a necessary condition for the piezoelectricity to exist. So, and the 20 of these are piezoelectric. So, one class, although lacking a center of symmetry, is not piezoelectric because of the other combined symmetric element. So, we have the symmetric element. So, on the basis of that we choose the piezoelectric material. So, piezoelectric material which we are choosing must be divided into the piezoelectric single crystal, piezoelectric polycrystalline and piezoelectric organic piezoelectric material. So, the material which we are using for the sensors may be piezoelectric single crystal, piezoelectric polycrystalline and organic piezoelectric material. The most used piezoelectric sensors are all kind of piezoelectric ceramics belonging to the piezoelectric polycrystal and the quartz crystal in the piezoelectric single crystal. Means we use the, whenever you use the polycrystal, so we use the ceramic, and when we are using the single crystal, then we use the quartz crystal. So the advantages of the piezoelectric ceramic are convenient firing, easy molding, moisture resistance, and the high temperature resistance. So we use generally the piezoelectric ceramics in the preparation of the sensors, and the high temperature resistance having this type of material. And the disadvantages of that, it has a pyroelectricity which will interfere with the measurement of mechanical quantity. Another type of piezoelectric materials is organic piezoelectric material, which include more than 10 kinds of polymer material, such as the polyvinyl iodine fluoride and polyvinyl fluoride, nylon, etc. we can use in the preparation of the sensors in the organic piezoelectric materials that we will use for the preparation of the sensor as per the requirement. Organic polyelectric materials can be mass produced and made into a large areas, and it has a unique advantages in matching the acoustic resistance of air, and is a new type of the electroacoustic material, and with a great potential for the development. Crystal with both the semiconductor properties and the piezoelectric properties are some are classified as zinc sulfide, zinc oxide, calcium sulfide, and have discovered in 1960. And using these materials, a new type of the piezoelectric sensors that integrates sensitive components and electronic circuits can be made in a very promising way and in a low cost. And in comparison of the piezoelectric crystal and the piezoelectric ceramic similarities, they are all piezoelectric material with a piezoelectric effect. And what are the differences between that? The advantages of the quartz is that the dielectric and the piezoelectric constants have the good temperature stability, making it suitable for the sensor with a wide operating temperature range. So the polarized, so the ceramic can be used in this case. So the polarized piezoelectric ceramics, when deforms by the external force, generate the charge due to the repositioning of the electrode movement. So the piezoelectric coefficient of the piezoelectric ceramic is dozens and even hundreds of times that of the quartz. So whenever we require the transformation, then we require the ceramic, but its stability is not as good as that of the quartz. Quartz are more stable as compared to the ceramic piezoelectric materials. So we require that as we prepare the sensor, so we require the sensing material which is having a high sensitivity, high selectivity, and high resistance, so that we require for the preparation of the piezo sensor. So three main group of the material are used for the piezoelectric sensors, which are piezoelectric ceramic, single crystal, and number third is the thin film piezoelectric material. Thin film piezoelectric material, because we are preparing a thin film, because we are preparing a, sometime it is used for the smaller devices, nano devices, so that is required. So the main group of the material which are used for the piezo sensors are the piezoelectric ceramic, single crystal material, and the thin film piezoelectric material. So we will discuss these sensing material in the next lecture, then how it works, how it trained, how we can prepare the piezoelectric sensors, and how these are divided into the groups and how it works Thank you very much.